509, Section 7, the magnetic force on a moving charge. The first thing I recommend you do is hit pause, go have a look through this section in your textbook. In Knight, that's pages 815 and 816. If you have a different textbook, that's no problem. Just look up the section about magnetic force on a moving charge. Physics hasn't really changed in about, 500 years, so whichever one you read should be just fine. So let's start with a reminder of something you did in Physics 1051. Let's see if this rings a bell. You made a little motor, a little DC motor, by making a little coil of copper wire, taping it to a bamboo skewer. Then you set it over a couple of magnets on a wooden base, and then you hooked it up to a power supply. If you followed your steps pretty carefully, you found that the little thing spun around and you were able to make some observations. So from that lab, one of the takeaways is that there must be a magnetic force on a moving charge or on a current carrying wire. So if the charge moves, there must be a force, and that force is the thing that made the motor spin. So that's the part we're going to look at next. What is that force? And it's really pretty interesting. It started as an experimental observation, and the experiments showed that we can find the magnetic force, FB we call it. If we think about a positive moving charge, we'll deal with negative later. So the magnetic force, if we have a charge Q moving with velocity V in a magnetic field that we label B, doing some different experiments similar to what you did in that motor lab, it shows that we can figure out what the magnitude of the magnetic force is proportional to. So what we learn is that the magnitude of the magnetic force, first of all, it's proportional to the charge. So if we change the amount of charge, we change the size of the force. And if we increase the charge, we get a bigger force. We also see that the size of that magnetic force is proportional to the speed. If the charge goes faster, it has a bigger speed to it. It's also proportional to the magnetic field, the size of the magnetic field, or the magnitude of the magnetic field. These things you might have fooled around with a little bit in that motor lab in Physics 1051. If you turned up the current, it turned faster. If you threw in another magnet, it also turned faster. So that force definitely depends on those things. That's not the only thing it depends on. Here's a pretty neat result. If the velocity and the magnetic field are parallel, then the magnetic force is 0. If the magnetic field and the velocity are perpendicular, or they at least have one component that's perpendicular, then the magnetic force is not 0. Okay, so together that says that the magnetic force depends on the angle alpha, where alpha is the angle between the velocity and the magnetic field vectors. Okay, that's worth stopping to think about just for a second. So let's see if we can put this in context of gravity. We can understand exactly what that means and kind of what that impact is. So gravity is something we're familiar with all the time. So here we are, we're just standing still. As we're just standing still there, so what if the force due to gravity was like the force due to the magnetic field? That's kind of a good question. So if you stand still, that means your velocity is equal to 0. You'd have gravity turned off. Okay, that's weird. And you would start to float. So you would start to move up. That's a pretty strange thought. So as soon as you stand still, gravity goes away and you start to float up in the air. Okay, what if you weren't standing still? What if you were starting to move up? Okay, as gravity turned off and as you started to float up in the air, what if that happened? Well, then you're moving parallel to the gravity and you still have zero force. So still no force due to gravity, still no weight if you move up or down. Well, what if you start to move sideways? As soon as your velocity went this way, you would fall over because gravity would then start to happen. So you move sideways, Fg is not 0, you fall down. If gravity were like magnetic fields, if the force due to gravity were like the force due to magnetic fields, we would live in a very strange world indeed. Everything about our life experience would change. Okay, so the main point to take away here is that magnetic fields are really weird. A charge will only have a force. First of all, it has to be moving. Second of all, it has to be moving sideways. Any other kind of motion, there's no magnetic force. Very strange idea. Okay, let's come back to this. So we know that the magnitude of the force is proportional to charge, speed, magnetic field, and the angle between the two guys. We also know that if the charge is negative, then the direction of the magnetic force is opposite, so it flips over. So we can summarize this result of our magnetic force in that the magnetic force is QV cross B. So it's the cross product or the vector product between velocity and magnetic field multiplied by the charge. That's if you want to do the cross product. You can also use magnitude and right-hand rule. So there's the vector product. If you wanted to do magnitude and direction, we know that the magnitude of the magnetic force would be Q times V times B times sine alpha, and you would get your direction with the right-hand rule. Pretty important to remember that that right-hand rule applies to positive charges. If you had a negative charge, you'd have to rotate your answer by 180 or flip. Okay, so that takes care of the theory. Let's do some practice with that right-hand rule next. Oh, we went off the slide there. I'll have to be careful with my zooming. So let's get some practice with that right-hand rule and getting the direction, and then we'll do some examples with some numbers.